Right, so we're going to go through section C and start off with the multiple choice questions. Right, we've got a identify the feature of the waveform labeled Z. Z is going from 0 up to a peak. Okay. No, this is not a form factor. Frequency is a measurement of 1 over time period. So no, the time period is essentially this point here all the way across to that point there, so it's a measurement of the time for one full wavelength. Okay, so it's not frequency, it's not time period, it's not form factor, it's just going to be amplitude. Okay, now identify the term that defines resistance to magnetic flux. Okay, it's not going to be hysteresis, induction, no permeability, no, it's going to be reluctance. Okay, reluctance is the only word that actually sounds like it is resisting. Bit of a giveaway there. Anywho, question 16. Question 16, the potential difference between two parallel plates is 75 kilovolts. Okay, let's change that to 75,000 volts. Alright, you got a distance of 0.025 meters. Calculate the uniform field strength between the two plates, give your answer in appropriate units. So I've already converted to get it into appropriate units, but for this we can quite simply go straight to our electrical field strength. And we're going to be using this formula here, E equals voltage over distance for a uniform electric field. As you can see, uniform electric field strength. Okay, so we're going to require the formula E equals V over D. That's going to be 75,000 over 0.025 meters. Spit out number using a calculator. 75,000 divided by 0.025. 123, so that's going to be 3 million. Appropriate unit, alright, electric field strength with voltage divided by meters, so it's going to be volts per meter. So let's go to the very bottom of the page. So it's going to be 3 million volts per meter. And that's going to be the units for that. Question 17. Oh, this is a nice one. State one factor that affects the electrical resistance of a conductor. Right. So we can look at. Oh, gosh, there's so many. We can talk about V equals IR. We're talking about resistance here. Things that can affect it is going to be voltage, current. But there are other formulas as well. We've got the resistivity formula. Okay. So resistivity. Resistivity is something that inherently links to the materials, so material of the conductor. Resistive, we've got the length of the wire. We've got cross-sectional area. Because after all, I'm looking at the formula R equals rho L over A. So we've got length of the wire, we've got resistivity, we've got area. So I'm using these two formulas which can be the answers. We've also got the idea that if something is ohmic, it follows the straight line of V equals IR. But if it's non-ohmic, it means the temperature can affect it as well. So I'm going to put temperature down. By the way, all of these will give you just 1 mark, and frankly, this is 1 marker, so I feel like we've overdone this. Okay, yeah, there are so many things that can affect the electrical resistance of a conductor, but those are the ones that just come to mind. These 5 coming from the 2 formulas up above, this one you can learn about in A-level physics a bit further on. Right, that all being said, we've got some well, the start of some interesting questions now. Right, let's just sort this out. Lovely stuff. Okay, so we've got 4.5 volts. We got a resistor 1. Well, sorry, I said resistor 1. It's resistor 5 actually, 56 ohms. We got branch A, branch B, 22, 47, 33, 100. Right. So we've got all of those individually. Calculate the total resistance of branch A. Well, branch A is in series. Okay, because it's in series, we're simply just going to add up the numbers. So we get 33 plus 47, that's going to be 80, plus the 22, it's going to be 102. So 22 plus 47 plus 33. That is a terrible plus, it looks like a times. So, put this in a calculator if you want. I'm very confident it's going to be 102 ohms, so I'm just going to write 102. 102 ohms, just there. Right, it says calculate the total resistance of the network. Alright, one thing that is definitely going to be misconstrued is the fact that this is not branched. Not branched. Okay, this part is. This part is not. This part links up to this quite nicely. Okay, so I'm going to treat this as the single unit and I'm going to treat this as the branched unit. So I'm just going to add up to 56 to the 102. I'm going to get 158. Right. 158. Ooh, I've just realised something actually. I don't want to do it in order. See, even I'm making mistakes. Right, let's do this correctly, shall we? My laptop's bugging out. That's good. Right, let's try that again. I need to solve this branch section before I can add this on because I've got to treat this separately. What I don't want to do is I don't want to treat this as a branched part. I need to add this last. We've got 102. Okay, 102. We've got 100. But unfortunately, because they are branched, I've got to put them equal to 1 over our total. Right. 1 over 102 plus 1 over 100. Right, now I've got that equals this, but that is 1 over RT. I need to do the inverse RT is the equivalent of 1 over RT to the minus 1. So I've got 1 over RT here to the minus 1 now. That's going to get me this, which is going to be 50. In fact, let's go back to this. Okay. Right, let's quickly explain. What I actually did was, in my head, I moved this around the circuit. And as a result, I sort of got a diagram, if I draw it out really, really badly. I sort of got something that looked like this, with the first one being there, then it then branched up like so. So I moved the first resistor all the way around to this point here. I then had the second, third, fourth there, and I had that one there, like that. And as a result, I then realised that because this is branched, I have to add them up to get rid of the branch. Then I could put it in series and then add up this resistor with that resistor. After all, when you're trying to add something in parallel, what essentially you're trying to do is you're trying to turn, like even with series, look, if you've got these three resistors here, you try to work out the total resistance. It's like saying that you've just combined them all into one big resistor. But when you're adding them in parallel, it's the same feature. You're just trying to get one big resistor after all, total resistance. So once I've got a total resistance over here of this branch and this branch, it's essentially just this in series. So then I need to go back to just adding them in a straight line, which is going to be this one and that one. But I only figured this out by actually moving this around into a position that made sense in my head, because otherwise a lot of people would actually just say, well, that is branched to this and this, therefore they must all be put into this form of equation down at the bottom here. Okay, so hopefully you can follow him. Anyway, what I'll do is I'll just quickly re-explain what maths I've done. I did 22 plus 47 plus 33 to get me 102. That was branch A. Branch B is 100, and because they are parallel, I had to use the formula 1 over resistor 1, which is going to be this top section, branch A, 1 over resistor 2, which was branch B, and that's going to equal 1 over R total. Now I can't just have 1 over R total, I need R total. So I did this section to the minus 1, which was what was put in my calculator. Okay, and as a result it spit out 50.4950495, which I've wrote down here. Now, that only gets me part of the way. I've still got to add my 56. Now, fortunately, it's linear. Okay, it's in a series, therefore it's going to be 50 point. Let's bring this back down so you can see 50.49500495 plus 56, and that's therefore going to equal 106.495. I'm going to stop it there. Okay, because there's no point going any further. Right, total resistance, therefore, write it as ohms and be done with it. If you need me to re-explain that, okay, leave a comment and I'll go back over that. Right, question 19, explain the effects of full wave rectification on an alternating current supply. Right, this is always a good one. This is the use of diodes. Hopefully you know about this. If not, go back and have a look at the textbook, and they could show you what sort of diagrams. Even Google it, what is rectification, full wave rectification. Okay, they can give you some circuit diagrams and they can help you there. Point being though, it can do a couple of things, but the thing that I always come back to is it produces a DC smooth output waveform. This is done as each cycle of the input converts to DC. So essentially we've got those pairs of diodes that then lap it around, and no matter which way, whether the AC goes, so AC circuit is flicking on and off both directions, and as it's going around it will then filter through to a set of diodes, and it will allow you to constantly have this bump, this positive bump of essentially a DC supply. Okay, so each time you have a negative voltage, it will actually turn it around and make it a positive voltage, so it's not this sinusoidal wave, it pops it back up. But that is question 19. As I said, go back to the textbook there. I'm sure there is plenty of stuff you can find in there for it, or just give it a Google, okay, for some circuits. Alright, question D. Fully charged capacitor is discharged through a resistor when the switch is closed. Let's convert this. This is 22,000. Ohms, this is going to be 33 times by 10 to the minus 6 farads. Calculate the time constant. Time constant, let's have a look for it in the formula booklet. Looking for time constant. Did I miss it? Got time period. I'm looking for a very short formula. There it is, time constant. At the very bottom, T or tau equals RC, resistance, capacitance. Quite simple. Convert my resistance to capacitance, times them together. So time constant is tau equals RC. So I'm going to plug these values in. 22,000 times by 33 times by 10 to the minus 6. And I'm going to get a value of 7.26. Okay, got to be in seconds because everything was in SI units. Right. When the switch is closed, the capacitor begins to discharge. When T is 0, the voltage across the capacitor is 12. Calculate the voltage across the capacitor after 20 seconds. Oh, this is an interesting one. Let's have a look at form booklet, see if there's anything in here. Oh, it's been a while since I've seen that formula in action. Right. We're going to be using voltage across the discharging capacitor, which is at the very bottom. VC equals Vs. E to the time minus time over tau. Okay. Siri, stop. Right. Let's write that out. VC equals Vs. E to the minus t over tau. Right. It's probably the first time I've seen this formula in a paper. Right. So we want VC. Yeah. Vs, which is the starting one, so that's going to be 12. Let's do 12. What's of E? Bracket time at 20 seconds. It's minus 20 over tau, which is going to be 7.26. Right. So yeah, this is the first time I've seen this calculation done in a paper. Very nice that we're actually using another formula other than the same old. So I've substituted everything in. This is going to be 12 times by E to the power of minus 20 over 7.26, and this is going to produce a voltage across the capacitor. So I'm just chucking in the values now, looking for my value of E. E is over here. Let's put a set of brackets in. There we go. Got a fraction in, so minus 20 over 7.26. Let's close those brackets up at the top, press equals. Voltage is going to equal, so VC, voltage is going to equal 0.7634444, so on and so forth. Then we've got the rest over there, not that we need it. I'm going to go to 4 decimal places, why not? So my answer at the bottom is going to be 7634. This is a voltage, so it's going to be in volts. Okay, right. Nothing more to that question. 3 marks, 1 formula, sounds about right. Time to move on. Ooh. Graph question at the very end. That's rare. Right, got coil, 300 turns is wound around steel core. Okay. The length has the core has a length of 0.9. Okay, well, that's all right. Before we just figure out all the information, let's figure out what we're calculating. I'm going to work backwards with basically mindlessly just plugging numbers into formulas and then going to get the correct answer. Okay, we don't need to actually know anything with this because I already see this is magnetism. And if this is a magnetism topic, we should be able to get away with just mindlessly putting numbers into formulas. Calculate the current required to create the magnetic flux of this in the core. We're looking for current. Okay, current. I'm going to go to my magnetism page. Here it is. I'm looking for something that gives me current. This gives me current. Do we have a magnetomotive force? I don't think we do. No, don't believe it's going to be that one. Probably going to be this one here, H equals Ni over L. So I'm going to quickly substitute that into the formula. There we go. H equals Ni over L. So we probably rearrange this to get our I. We have a length, 0.9. We have N, number of turns. We have H. Well, we've got a H along the bottom here, but we need to specify what H we have by this. How do we get this? Right, okay, I see a formula that we can use. We've got B equals that over A, so there's a potential there. So that gets us our B value. Do we have a cross-sectional area? We do have a cross-sectional area. Right, lovely. Okay, so we've got everything we need then. We've got cross-sectional area. Do we have the value B? No, of course we don't, because that's what we need to find on the side. We've got that. Okay, yeah, we've got absolutely everything we need. Right. So, let's just break down my thinking. We said calculate the current. I found a formula that had current in it with some of the other things that we've been given information for. So we've got length, which is 0.9. We've got N, which is the number of turns, which is 300. We don't have H, but we've got this graph that has H, and we've got this data plot. So say that H was going to be 3000. I'd find it at this point exactly there, which is between 0.5 and 0.6 lots of B. Okay. The first thing I need to do though is find out what value of B I need, so then I can work backwards and go this way. I've got this value, 0.1 milliwebers, so I'm going to change that to 0.1 times by 10 to the minus 3, and that's going to be in webers, so that's SI unit now, so very useful. My cross-sectional area is already in SI units, being meters squared, so let's get 0.1 times by 10 to the minus 3 divided by 250 times by 10 to the minus 6. Let's see what we get. Calculator, let's get it into, there we go, 0.1 times by 10 to the minus 3, all over 215 times by 10 to the minus 6. This is going to get me 0.4. That's nice and easy. So B equals 0.4. Find B with 0.4, track it along on the graph. Hits basically at 1500. Okay, we don't need an exact science. The examiners are going to understand it's not exact science. They're going to expect you to just give it a round number, which is going to be at 1500. So because that equals that, H must therefore equal 1500. If H equals 1500 equals N, which is 300. That's fine. I'm substituting all my numbers into this, divided by 0.9. And from here, times both sides by 0.9 to get rid of it, so get... Okay, so that's the left-hand side so far. And we're going to have to, we've got 300 equals 300i, so I'm going to have to divide both sides by 300. Equals I. And I can already see that this is going to be 5 times by 0.9. 5 times 0.9 is going to be 4.5, but got a calculator here, might as well do it. That's 1500 times by the 0.9 over the 300. There you go, the 4.5 that I was just on about. And that's going to be amps. Right, as I said, no explanation in terms of like how to do magnetism. Simply just look at it as a case of, oh right, I'm just plugging in numbers into some formulas. Okay. You don't need to know everything about this topic just to get marks. That's really what I'm trying to get at. Right, and that's it for this paper. So, if you have any questions, please leave comments and we'll get to you. Other than that, I'll see you in another video.